In this video, we are still simplifying rational expressions. This time we're completing them from the advanced portion of the Khan Academy set of questions. Here again we have a rational expression which is made up of a polynomial divided by another polynomial. The major difference here is that we have results that contain a second variable. Now, a lot of times I'll tell students just to ignore that second variable. Just throw those out for a moment and see if the existing expression looks like something that you could handle on your own. And I would say that this should be just fine for z squared plus 4z plus 4 and 4z plus 8. Hopefully you recognize that in the numerator we have a standard trinomial. So z times z would give us z squared. 2 times 2 would give us 4, and a 2 plus 2 would give us a positive 4 in the center. In the denominator, there's a GCF of 4, which leaves us with z plus 2 after factored. This factor and this factor can cancel, and we now have z plus 2 over 4. Now that would be the case if we didn't contain this y component. As it turns out, and many times, if there is a y component, we can still use essentially the same techniques. The only major difference here is we have to ask ourselves if z times z would equal z squared, then 2 what times 2 what would give us 4y squared. And that's easy. That's a simple fix. 2y times 2y would give us 4y squared. And also, when we FOIL this back together, z times 2y is 2yz, or 2zy. And 2y times z also gives us another 2zy. When we add those two together, we get the 4zy that we were after in the first place. So by simply adding in or reintroducing the y variable in the at the end of each binomial, we've got this accounted for. In the denominator, the same thing is true. If we had 4z and 8y as our denominator, well, the only common factor, again, is the number 4. But what's left over after we factor out a 4 from 8y is not just 2, but 2y. As it turns out, z plus 2y is the common factor that can be canceled in the numerator and denominator, so we'll go ahead and do that. And what we're left with is z plus 2y over 4. I answered this result off camera, and it was accepted by Khan Academy. But looking at the next question, it's a bit different, so I'll include that on the screen now. In this next question, it looks a bit intimidating at first, but in all honesty, we use pretty much the same process as we have been for this entire unit. If we can find a common factor first, I would suggest that we factor that out, and then from there, try using our standard trinomial factoring techniques. So in this numerator, for this polynomial, I do see that 3 is common to both terms, but I also see that both terms have a collection of z values that are common. And I can equally or evenly divide 5 z's from both terms, and I would be left with, let's see here, 3z to the 11th. I'm thinking in my head, 3z to the 11th divided by 3z to the 5th. Well, I know the 3's are going to go away. Z to the 11th divided by z to the 5th would require a subtraction of exponents if the bases are being divided. So that leaves me with z to the 6th power. And then for the second term, similarly, 3z to the 5th factored by 3z to the 5th is simply the number 1. Now in the denominator, this is a bit different. It's definitely a trinomial because it only has 3 terms, and it kind of looks like a standard trinomial because we have no leading coefficient, or at least nothing on display. The leading coefficient is 1. So what would happen if I treated that like a standard trinomial? Could I find 2 terms that multiply together to make z to the 12th power? Well, certainly, lots of combinations work. Z to the 11th times z to the 1st, z to the 10th times z to the 5th, or I'm sorry, z to the 2nd, and so on. We've got lots of different combinations that would work, but also let's keep in mind that in a standard trinomial, the leading term of each of these binomials is always the same. So let's go with z to the 6th times z to the 6th. When the bases multiply, the exponents add, and we're now back to z to the 12th power. For the second term in each of our binomials, I'm looking for two numbers that multiply to make 3, that would add or subtract to make 4. And that would be 3 and 1. And a positive 3 and a positive 1 at that. And this is pretty nice because I do see something that's going to cancel when it comes time to factor. But let's just double check some things real quick. Z to the 6th times z to the 6th is z to the 12th. Z to the 6th times 1 is z to the 6th. 3 times z to the 6th is 3z to the 6th. And then 3 times 1 is 3. When I combine these two like terms, I'm now left with z to the 12th plus 4z to the 6th plus 3. And indeed, that was the original trinomial that we had in the denominator back here. So all of that red ink was just done to verify that we did factor correctly. So before I go any further to simplify, now's the time when I always check for my excluded values, or the values of z that make the expression undefined. That occurs when each of these factors that are in the denominator currently are set equal to 0. So when z to the 6th plus 3 is set equal to 0, we can subtract 3 from both sides. And then to isolate z, we could take the 6th root of both sides of the equation. And that tells us that z would be equal to, and since we had to introduce our symbol here, we'd have a positive and negative result, the 6th root of negative 3. Now, this is a non-real solution, non-real number. We can't take an even root of a negative number. So the correct answer would imply that there are two non-real solutions that make the expression undefined, but the question did specify to say which real values, which real number values of z. So these don't count. I'm not going to use those as an exclusion. For our second term, we have z to the 6th plus 1. That should be set equal to 0. And I'll kind of separate these because these are two separate tasks to complete. We'll again subtract 1 from both sides to get negative 1, and in a similar fashion we see that z is equal to the positive and negative 6th root of negative 1. Again, non-real solution, so we can't say that there are any real values that make the expression undefined. As far as our simplified answer goes, well, now I'll come back up here and I'll consider these factors that cancel, and I would report that 3z to the 5th over z to the 6th plus 3 is our reduced, simplified final answer. I did check these answers on a separate screen, and they were accepted. So I think that's a good approach for these types of problems. I hope this video helps. If you have additional questions, please be specific and let me know. Thanks for watching.